Can you cut these lights up here up in front? Good. We've handed back your printouts, and as I mentioned, if you didn't get yours, if you're a little slow getting up here, we'll catch you after class or first thing on Thursday. I have a couple other things, this and that, to go over with you. First of all, your participation data is up as of Thursday last week, the 26th. All right, now for this class, there were, on the books, you've got 23 official questions since September 5th, lecture 4. So you're participating, and you might want to write this down. If you want to figure out your grades and stuff, I'll show you how to do it. Your participation percentage is how many you answered out of 23. So whatever number that is, n divided by 23. And then you put that into this proportion, and this is the same one that's on the syllabus. You solve the proportion, your percentage goes in the numerator, and then you solve for your points. And that's how you figure out your pointage. And so that's a fraction of 45. So, and I just I calculated this out for everybody. There's like 40% of you that are above 85% participation. You don't even have to do this. All right. For those of you that are below it, yeah, you have to do it. Question over here. Yeah, that's right, and that's because the afternoon section has 24. I might just remove that, but and I'll just make it out of nothing. But yeah, the afternoon section has one more question. I'm going to try to even that out today. So, but anyway, so for you guys, you divide by 23. So whatever you have on, and that's the answers. Now the correct is also out of 23, but that goes into your bonus point calculation. And we're not going to dip into that too much today. Anyway, so if you have a friend in the afternoon, they've got 24. But I think by the end of today, it'll be caught up. It'll be straightened out. It happens sometimes. Okay, now, the other thing I want to review with you is we haven't had a whole lot of homework inside web courses, but it's a straight percentage. And right now, as of today, there's 25 points possible. Now, don't include homework 0. That was just the attendance quiz, so we don't factor that in with regular homework on stars and stuff like that. Okay, so just take up your scores for homework 1 and all the way up to, I think it's homework 8, and then just add them up. And then divide by 25, and then multiply that'll be your percentage. Then multiply that by 10, and then round up. So here's an example. If you have, for instance, 21 out of 25 on homework, then that's 84%, 0.84. Multiply that by 10, that's 8.4. And then round that up, and you actually get 9 out of 10. Now, any questions from the student body about this or about observatory questions? Go ahead. The observatory? Yeah, how do you let me know if you've gone to the observatory? Actually, you don't let me know. You give the observation sheets to the guys at the session, and then they give it to me. So they're the ones that actually let me know. And we just handed back Buku observation sheets from October 11th. Those are graded. I haven't gotten the ones from Sunday yet. Maybe this week, maybe next week. And as soon as we do, by the way, I think there's one Wednesday. Is that correct? And hopefully you'll have another shot at going to observe. And on Wednesdays at the observatory. And so it'll be a little bit different. What did you guys think of? What did you guys look at? Those of you that were Sunday night, I was thinking about going, but I didn't get to it. What did you guys look at, other than the moon? What did you look at?
Saturn
Albireo. Okay. Oh, so you looked at Saturn and Albireo again. But you looked at the moon, though, didn't you?
Yeah.
What did you see on the moon? Craters and stuff? All right. So the procedure is, so you can't bring it to me. And I had somebody yesterday say, Dr. B, can I drop this? No, you got to give it to those guys at the session. So try to remember that. Yeah, take your earphones out and listen. If you do go to the observatory, give it to those guys, the UCF Astronomical Society guys. They're the ones that run it. They'll get it to me. All right. Now, did you have a question?
Yes. I was just wondering how the extra credit points are factored into our final grade. Is it just added at the end?
Yeah. The question is, how do the extra credit points factor into the final grade? Well, I wrote a discussion posting in discussions about it. You can look at that, but I'll give you the basic specs. It's kind of like a peanut butter and jelly sandwich. Okay? When you make a peanut butter and jelly sandwich, you have all kinds of different ingredients. You have bread, you have peanut butter, you have jelly, and anything else that you put in with your peanut butter and jelly sandwiches, like pickles or whatever you know. So you have this stuff, and you put it together, but then by the time you eat it, it's all smooshed together in your stomach, right? So for us, the bonus points that you get from observatory or early iClicker registration or any other thing, they're just kind of a separate ingredient. And what they do is they go into the numerator of your grade, but not into the denominator. So for instance, previous to exam 3, we had some homework, we had some clicking, and we had one exam. Okay? And so that means we had a total of 105 points possible. But now we have a total of 155 points possible. Okay, that's the denominator. All right? So, but when you add in some bonus points, it's not like when we add in exam 3, we go up to the denominator of 155. You don't do anything to the denominator. You just put an extra couple points. Now, so the bonus points are just out there. I'll add them in on the numerator at the end of the semester. And you can kind of mentally add them into whatever your regular pointage is. Another way that you could think about them is just think about them as being attached to your final exam. Because, we're going to drop, hopefully for most of you, 1 out of your 3 midterms. All right? So keep the best 2, drop the lowest. All right? And we got homework. And homework is tricky, it's a percentage. And clicking is even trickier. It's, this 85% business, proportion. So I always say, if you're wondering where the bonus points go, just think of them as being attached to your final exam. So if you get 73, let's see, our final exam is 105 now. So if you get 75 out of 105 on the final exam, but you have 10 bonus points, it's like getting 85 out of 105. All right, you can think of it that way. But the peanut butter and jelly analogy is, the basic idea. It's all going to get smushed together by the end of the semester. I normally don't calculate any grades based on bonus points until after the final, because I'll probably put some bonus items on the final. Clicking bonus. Usually I do that through the clicking part of the test. All right. So I don't really calculate your grades. I'll sit down with you in office hours and go over your grade with you. But usually what I do is figure out your regular point grade and then just say, all right, now officially that's what your regular pointage grade is, estimated right now as of today. But you've got bonus points, so it's actually a little bit higher. But we're going to hold off on that until the very end of the semester when everybody's bonus points are set. Is that a good answer? All right. Question.
How many total points do you have right now?
How many total points do we have right now? I just said it about 2 minutes ago. 55 points, right? No, 155. Yeah, so we have two exams, 50 and 50. We have 45 points through this calculation up here for participation, and then 10 points for homework for this calculation. So, all right. Another question. And get your clicker out because we're going to do some clicking. And I'm going to give you some examples. But one more question. Yeah.
So in order to try to get an estimate of our grades right now, what we can do is just add up our total points and divide by 150.
Divide by 155, yeah. 155. And that's about the 19th time I've said it this morning. Anyway, so yo, in the back, yo. Okay, so these are the two tricky parts of your grade. I mean, they're not that tricky, but the exam points, you just add them in straight. Although you don't know what your total exam 3 is yet, because I haven't done the clicking for that. By the way, somebody had a question about the clicking on exams. Who was it? Before class came up to me and asked me about it. Okay, the exam 3 clicking, I'm still kind of sitting on it. It's not graded, but I'll put that in there. Probably, I might do it tomorrow. All right, let's try a few examples with iClicker. First one is doing participation pointage. All right, now I just went through the example with you. Let's do this one, or I'll let you guys do this one. Based on 14 out of 23. All right, now most of you are, a good pile of you, not the majority, 40% are above 85% already. So, but for those of you that are below 85%, you're going to have to do something like this. So go ahead and click that, work that out. 60.87%. I already figured that part of it out for you. Now you just got to solve the proportion. All right, so do that. I'll give you a minute or so to do that. Can you give me the 2 envelopes? Boy, this is good. We've got rid of a lot of these. Actually, no, I don't want to fix it. Okay, 30 seconds. And I'm going to go through the calculation with you step by step, so, but try to do your best. 20 seconds. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, go ahead and let's take a look at that. Go ahead and switch to that. We got a little bit of confusion here. Switch back to laptop, please, and we'll go through this. I just created that by hand. Sweet. Yeah, let's go through it step by step. Here we go. First thing you got to do is set up your proportion. And there it is, 60.87% as a decimal, 0.6087 in the numerator. And then your nominal threshold percentage, 85%, that's in the denominator. And then your pointage is on the right-hand side on top. That's the letter X here. And then out of total possible is 45. Okay? So, that's your proportion. And what you can do, what I normally do is I just do the quotient first. So 0.6087 divided by 0.85. And then you cross multiply. So you've got, let me get my cursor over here. Right, so here's your quotient, 0.7161. All right, and then you cross multiply, get 45 over to the left. Okay, and that's going to give you your pointage. All right, and so if you do that, it works out to 32.2245. And so the correct answer is 33. And don't forget to round up. The only time I'm a nice guy during the semester, and this is a calculation, a temporary calculation now in the middle of the semester, but it's not official until I do it at the end of classes. But I'll always round up, even if it's, this one's less than 0.5. I'll always round up. Okay, Jordan, did you have a question about that? Yeah, and it's just me being a nice guy instead of rounding down to 32, and then having a bunch of students. Oh, Dr. B, can I? I barely made it. So I always round up just for, to save a lot of distress. Okay, questions on this before I continue? We have another calculation to do. All right, so what this means, now that you're not asking me any questions about this, what it means is that you're going to never ask me about my clicker points, your clicker points. Hopefully. Not. I know it's not going to be. But anyways, this is how you do it. So, but if you're a little nervous about it still and you want to go over, just come to office hours or catch me after class or something and we'll take a look at it. It's not too bodacious. All right, let's do a homework calculation. Here it is. You've got 19 out of the 25 so far. What's your homework pointage? Go ahead and get this. This is a cinchy one. But we'll go through this one step by step as well. All right. And actually, I shouldn't have the CPS or the iClicker on there, but Alex, I want to talk to you after lecture about something. "30 seconds. "10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Better show this one. We got some splaining to do on this one. So if you biffed it, let's go through it step by step. All right, so step number uno, 19 out of 25, that's your performance percentage on homework. Multiply that by 10, and you get 7.6. That's it. I just saw a bunch of people going, oh, like this. Were you trying to do it like clicking with a proportion? I hope not. This is all you got to do. Just multiply by 10. And then, of course, round that up. So the correct answer here is 8. Did you get that?
No, I didn't.
Okay.
I'll do it.
Yeah. So yeah, that's the correct answer on this one. Okay, so just remember how to do that, and we'll be good. So exam 3 clicking is not finished, but add that into your Scantron score, whatever you do get, and I'll try to post that as soon as I can. And I'll activate the row, your row in grades, the grades page with your Scantron class sometime about 2:30 or 3 o'clock this afternoon. Okay, so remember that you've got a little bit more, hopefully a little bit more pointage coming on the exam. Okay, final questions on exams and so forth. Yes?
So how do we add it into our exam? Points?
Repeat?
How do we add the curriculum to the exam?
How do you add them?
Like, how do you add it in? Like, do you rate the points and then?
So, yeah, so what you're doing right now is estimating your grade status as of October 26th, all right? So you figure out how many homework points, just like we just did. You figure out how many clicker points, just like we just did. And then add your 2 exam scores, and then divide by 155. And you're looking at 90% for an A, 75% for a B, 60% for a C, 50% for a D, below 50% is an F. So, and by the way, let me just to reemphasize, the clicking percentage, or excuse me, the clicking pointage is going to be a nice chunk of change for everybody in here, most everybody in here. Because right now it's like 41% of the class, you've already got 45 out of 45. You're above 85% participation. A lot of you are 100%. And that is going to be like 45 out of 45 on a mid. Okay, our midterms are 50. So let's see, that would be like a 45-point midterm, and you aced it. Okay, and so it's really nice. And you won't know exactly what you have for your semester grade until the end of the semester when we finished all our official clicking, but for many of you, it's going to be really nice. All right, let's go back to the sun. We're talking about energy, and last time we talked about energy in general. I gave you an example with, for instance, a Bumblebee Camaro on a quarter mile. At the end of the quarter mile, at 115 miles an hour, its kinetic energy was 2.2 megajoules. Its average power, 176 kilowatts. So, and that's an energy production rate. We rate the luminosity of stars like the sun in watts, and it's many, many orders of 10 higher than that, but we still use watts. And there's other ways to rate the luminosity. Now, in matter of fact, one way to rate the luminosity of another star is as a fraction of the luminosity of the sun. So if you know the luminosity of the sun, you can then relate it to the luminosity of everything else. So, a star with 10 times the luminosity of the sun would be 10 solar luminosities. That's another way to do it. We talked about rest energy, and specifically using the famous formula E equals mc squared. How much mass goes into the sun's energy per second, and we also did per year. And we found out that a certain number of kilograms of mass go into the luminosity of the sun per second, and another number per year. And we found out that per second, that's about 2 parts per sextillion. 10 to the 21 is a sextillion. Okay, so it's not a quadrillion, it's not a quintillion, it's a sexotillion. And so 2 part. So it's a minuscule. Even calling it minuscule is overemphasizing. It's just really, really submicroscopic. We talked about the Kelvin scale, and here's an example. And you're going to have a clicker question about this in just a second. The Kelvin scale, where compared to water, you have a difference of 273 degrees. So 100 degrees boiling for Celsius is 373 for Kelvin scale. 0 degrees for freezing water on the Celsius scale is straight 273 on the Kelvin scale. And then 0 degrees Kelvin is negative 273 on the Celsius scale. So it's a metric size, it's a metric scale. It's got Celsius size degrees. There's still 100 degrees between melting and boiling water. But the 0 point is way down there at the limit of molecular motion. We talked about Roy G. Biv concepts, and the red, orange, yellow, green, blue, indigo, and violet. And we're going to talk a little bit more about that today, actually, because we're going to talk about Doppler shift. The railroad train, that shift in the frequency that we listened to a few minutes ago on YouTube, is a Doppler shift for sound. And we're going to talk about that in terms of electromagnetic radiation in just a few minutes. But before we do that, let's do a simple Kelvin scale temperature calculation. You ready? Now I'm going to give you a multiple choice question here. Go ahead and start this one. Okay. And go ahead and convert 37 Celsius. That's 98.6 Fahrenheit. But remember how to convert? Look at your notes. Actually, look at the diagram. If you look at that diagram, you should be able to reason it out. Look at your, and as always, read carefully. That is slick. Can't do it on this one. Yeah, it's pretty nice. Dell. Okay, 20 seconds. Let's see the number of students that are. That's good. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, let the students see this one. Yeah, you guys are geniuses. So it's, but I guess a few of you got tripped, so let's just double check that. Basically, your theory is to go from Celsius to Kelvin, you add 273. So you can kind of see it in these two parts. I mean, you can see it everywhere. But yeah, that's the deal. So the answer is B. Here's another thing that I want everybody to add, even if you got it correct. Another thing to remember, and this could actually help you on a multiple choice test, any physical object has a Kelvin temperature that's positive. There's no physical object below 0 on the Kelvin scale, right? There's plenty of objects below 0 on the Celsius scale and Fahrenheit. That's no great shakes. But the way that we've set up the Kelvin scale, it's always a positive temperature. The reason for that, or one of the reasons for that, is that the energy, for instance, the energy of a gas, is tied up in the kinetic energy, 1/2 mv squared for all the little zillion atoms and molecules of gas, whether it's oxygen or nitrogen that we're breathing right now, or CO2, anything like that. It's in the kinetic, and the kinetic energy, 1/2 mv squared, is always positive. So having a temperature scale that never goes positive or that never goes negative is one of the things that's nice about the Kelvin scale. I want to reinforce with you now, so these are new notes, about the E equals mc squared. Now, we talked about that, we worked it out. And let me just give you this one. 1.0 gram of anything converted into pure energy is about 90 trillion joules. So that's a lot of energy. All right? So 90 trillion. So you can figure, so take the most powerful hydroelectric dam in the United States and just let it run, and take all that energy and convert it back into water, or convert water from some other lake and so that it equals your hydroelectric dam. So for instance, Grand Coulee Dam, the rough capacity, if everything's running, if they're running all the turbines and everything, is about 6.8 gigawatts. So they could run several flux capacitors, and like 5 flux capacitors, which is what makes time travel possible, and still have some energy left over. All right. Now, if you let Grand Coulee go, at full capacity for the entire age of the universe, right? So this is kind of fanciful. But if you gave it as much time as we have so far covered from the Big Bang up until today, that's about 13.8 billion years, we figure. And so if you convert it back into matter, take all that energy that it generates, 6.8 gigawatts times 13.8 billion. So that what is that? 6.8 times 13.8. Somebody calculate that. That's like about 100. 6.8 times 13.8. 90 or 80 something. What is it?
93.4.
So 93.84. Anybody verify that? Yeah. Okay. 93.84. Okay. So that's about 93.84 billion gigawatt years. Oh my goodness. So that's a lot. That's a big energy bill. So if you convert all that energy back into pure matter, gram by gram by gram, you know how much water that's equivalent to? About 157th of Lake Okeechobee. That's what I want you to write down. Our most powerful dam in the United States, the Grand Coulee Dam out in Washington State on the Columbia River, 6.8 gigawatts. That's the biggest hydroelectric dam we've got. And there's a few bigger ones, I think, over in Russia, over in Siberia. I think they got a really big one in China, if it's all working properly. But even if you ran it for the age of the universe, it's just this much water. That's not even a spit in the bucket. It's not a teaspoon in the ocean. It's zip zap. And that's the biggest that's about the biggest we got. And it's just amazing the amount of energy a single gram of matter can offer you if you convert it to energy. And that's what the sun does. So when we see E equals mc squared, we're talking about an enormously efficient, hugely efficient energy production method in terms of how many grams it takes to make a bunch of joules. So a very small fraction of Lake Okeechobee, and that's about the biggest lake that we've got here in Florida. So it's kind of amazing to think about. All right, now let's go back to Doppler shifts. Talk some more about this. I love this picture. This is a Dopplergram. And down at the bottom, you can see that over here, there's a rating of negative 2,500 meters per second. And over here, a rating in white, positive 2,000 meters per second. We're going to be talking about that. All right, so let's review what we saw for the train. Okay, now at rest in the switch yard, you're just sitting there and the locomotive's waiting for the engineer to come, and the fireman, blows, hey, blow the whistle, and the fireman goes, he goes like this, he blows the whistle, and that's your normal frequency, your normal pitch, okay? Now, when it's coming toward you, the pitch you hear is higher than what you would hear at rest with respect to the train. So in other words, either traveling at its same speed or at rest with the train in the switch yard. So if the train's going 60 and you're on a parallel road, which you can sometimes, sometimes the road goes parallel to the railroad tracks. And so the train's going 60 and you're going 60, you'll hear the same frequency that you would if it was at rest in the switch yard and if you were just standing there at the switch yard. But if it's coming toward you, the observer, the pitch is a little bit higher, and that's what we heard. And we especially heard it once it passed, because once it passed the rail fan, now the train is moving away from him, and you can hear the pitch go down. That's really the shift that you hear. And my wonderful students, that is known as a Doppler shift. Okay? That's a Doppler shift for sound. Right? Now, you can read all about that on the internet. I want to focus on the Doppler shift for electromagnetic waves. And because this is a really, really useful tool, or it gives us a really, really useful tool for studying stars and basically for just about studying anything. Matter of fact, the Doppler shift for electromagnetic waves is also useful to the cops when they're looking for speeders. Now, I know that everybody in here is a nice young person that never disobeys the speed laws. You never speed. You're not maniacs. I know this. I trust this. So you never get tickets. But I, your faithful instructor, have gotten a few tickets in my life. And it's always because of the Doppler shift. Because when you measure light, for instance, if I'm driving away from the policeman, or if the star is moving away from Earth, it's got a motion in space, it's moving away from us, the frequency decreases, just like it did for the train. Once that train passed the observer, the sound went down, Sydney, quite a bit. All right, and we noticed it. Now, when the sound, when the frequency decreases, the wavelength increases. All right? And another way that we would say it is the color of the light, the color of the radiation reddens. We call it a redshift. All right? Now, a side note for the sound, the Doppler shift of sound. For sound, the pitch that you hear is actually the frequency. So higher pitch means higher frequency. All right, so a middle C, the A above middle C is at about 440 cycles per second. So that means 440 sound waves hitting your eardrum per second. It's basically a pressure wave. So the pressure, the air pressure next to your eardrum increases, decreases, increases, decreases, increases, decreases, about 440 times per second if you're listening to the A above middle C. Okay? Another way to describe that is in hertz. So the symbol Hz is the metric unit, or denotes the metric unit for frequency, which is hertz. Cycles per second. And they named it after a German scientist named Professor Hertz, Hertz. So that's what, now we're going to talk about wavelengths for electromagnetic radiation. All right, so let's keep going with this. So the observer, is moving away. The color reds, we call it a redshift. Now, if the source is moving toward the observer, okay, so this is me moving towards the policeman, or a star, or a part of a planet, or a part of the SUN is actually moving towards Earth, then you hear a larger frequency. All right? And so the wavelength gets smaller. So a blue shift means a smaller wavelength, higher frequency. All right? Now, I'm going to give you an example here of what that means, blue shift and red shift, in terms of our beautiful red H alpha line. Okay? In the lab, the wavelength of the H alpha line is 656 nanometers. Okay, you can figure it out by doing a little bit of trig and having, a fairly good meter stick and stuff. I've done it. Have you ever done that? Measured a wavelength in the lab?
No.
With a laser or anything? It's pretty easy to do. And just as a side note, a nanometer is a billionth of a meter. Okay, frat boys dismissed. So if I say that the source is moving away, you might see a longer wavelength, so maybe 658. So make a note of that. That's a redshift. Slightly longer. So we would say that that's deeper into the reds. If it's approaching you, it might be a higher frequency, shorter wavelength, so it might be 653. And the key is that each wavelength that you measure, or alternatively the frequency of the photon that you measure, that gives you the speed and the direction. So make a note of that. That's really our leverage for studying this. Now, here's the same basic information. Technically, 658 and 663 are still in the red R region of Roy G. Biv. All right, but we still use the word shift. 658 is a little deeper into the reds. And 653, it's still red, but we'd say it's a little bit, it might look a little more orangey, but that's in the direction of the blue, so you call it a blue shift. Okay? So anytime you have something moving away, and the thing is, we see red shifts and blue shifts in ultraviolet, which we cannot see, that doesn't have a color for our eyes, but we still call it red shift and blue shift. Okay? We see it in infrared and radio waves. We see it in X-rays from various X-ray sources. So that helps us to decide what's going on. As a matter of fact, that is our leverage for analysis. All right? So emphasize item 3. Each lambda measurement reveals the speed and direction, or no speed and direction if it's at rest. It'll reveal to you that you're at rest. So let's take just a minute and look at some Doppler shift in our solar observations. Now, this is a Dopplergram for the full disk of the SUN, produced by the SOHO satellite. Here's a close-up of it. And you can see here that the dark area signifies a minus 2 kilometers per second. And what that means is it's moving away from you at 2 kilometers per second. And over here on the right side where it's lighter color, that means it's positive 2 kilometers per second. That means it's moving towards you at 2 kilometers per second. Here's another one. This is a figure from your textbook. These are convection cells in the surface, and we know that they're convection cells because we can measure the Doppler shift for each little grain, each little cell. Now you may be saying to yourself, Dr. B, how can they possibly see those little grains? Well, it just happens to be that the size of those grains, the size of those convection cells are basically the size of Texas on average. So they're pretty big compared to us. They're pretty small compared to the SUN. All right, it's 10:20. Let's dismiss. I'll see you guys on Thursday. We'll talk some more about convection. All right, now here's the, can you turn the lights on up here? Come on up if you want to get your printout. All right, great. All right, now, shutdown procedure. First, turn off the recording.